Yo, what up, YouTube? Welcome back to Learn with Earthquake Dude. This is lesson 6. We are transitioning into a new chapter, or chapter, but a very intriguing one in plate tectonics. Okay, so really excited for this. And before we begin, please make sure to drop a follow on my TikTok, Twitter, and Instagram, Earthquake_Dude. But without delaying any longer, let's get into it. You guys gonna enjoy this one. So I want to start off by showing you this map. Okay, now what you're looking at here is a global distribution of earthquakes. Okay, now just look at it, take a second and tell me what you see. So what I wanted you to see here is that all these black spots that you see, that those are earthquake epicenters. Now what I want you to see is that they're not randomly distributed. Okay, they happen in specific areas, and that there's a reason for that, right? So some of the simple observations we're going to make here is that some of these earthquake epicenters actually coincide with these mid-ocean ridges, these large mid-ocean ridges that are underneath the ocean, that are underwater. Okay, but these these earthquake epicenters also coincide with some of these deep oceanic trenches that you see here. All right, so then that's not random. That's there for a reason, right? And then the last observation I want you guys to see here is, if we were to cut off the ocean, the Atlantic Ocean, between South America and Africa, notice how those two continents would fit perfectly like a piece of a puzzle. Huh. Ever noticed that? So there's a reason that happens, okay? And that's because we are, in fact, on top of specific tectonic plates, right? And this is what a map of today's current tectonic plates look like. Right, there's a Pacific plate, there's a North American plate. I'm from California, so you see California is right there. We see our beautiful San Andreas Fault there. But you can see everywhere on Earth, we're made out of these large tectonic plates. And you'll see how this transitions into earthquakes. But I just wanted to give you guys an overview of what plate tectonics look like. And if we compare that to the distribution of earthquake epicenters, you could see that these earthquake epicenters clearly map out these large tectonic plates. Right, so that's what I wanted you guys to see, how the beginning of plate tectonics, that's what we use. Epicenters of earthquakes, volcanoes, where we saw mountain buildings, things like that. Right, so let's get into the two main parts of what plate tectonics look like. So essentially, the Earth's outer shell is divided into these rigid plates that move relative to each other by gliding over a weaker layer. Okay, now you're separating two different layers. You have the lithosphere, which is the rigid shell that contains the plates, and that can range anywhere from Earth's surface to about 100 kilometers deep. Right, that's that really brittle, that's the rock that you see, that you stand on every day. Below the lithosphere is the asthenosphere. That's the weak layer that the lithosphere glides over, or the plates glide over, and that ranges anywhere from 100 kilometers to 50 kilometers. Okay, now we know these exist, and then we can talk about why or how we calculated them, and that has to do with seismic energy of earthquakes. But let me give you an analogy, something that'll make it kind of clear. So I went funny story, I went to a buffet, and I was eating some bomb shrimp and stuff like that, but it had a really cool candy buffet bar. Anyway, so they had some cookies, and they had some jello. Okay, and I said to myself, let me make this diagram because it could explain what the lithosphere and asthenosphere kind of looks like. So here, the cookie, you can imagine a cookie like the lithosphere, right? If you were to bend a cookie, it would break, right? It has that brittle behavior. That's the plates. That's the lithosphere. And above the cookie, gliding on top of it or below it, is the asthenosphere, and that's your jelly-like texture, right? Again, you could bend jelly, right, and it's not going to break. It doesn't have that brittle behavior. It's more ductile, right? More plasticky, more bendable, more malleable. So the cookie is the lithosphere gliding on top of the asthenosphere, right? So the lithosphere, essentially, these are your large tectonic plates, and at that boundary where the cookie breaks and the two pieces are coming together, that's the plate boundary. That's where you get earthquake, mountain building, and tectonic activity. So I hope the food analogy made it a little bit easier to understand, because I always like making. So let's look at the inner structure of Earth, right? Again, we have oceanic crust, continental crust. We see the lithosphere. This is where the tectonic plates are part of the lithosphere, and they glide over this weak asthenosphere. The lithosphere, asthenosphere, mesosphere, right? And here you can see the inner core, outer core, crust, mantle. So just to give you a heads up, the lithosphere contains both the crust of the Earth, but and the top part, the upper top part of the mantle. That creates the lithosphere. That's what those are what your tectonic plates are made of. Really, really intriguing. Now that we know what tectonic plates are, when two tectonic plates come into contact, that's what's known as a plate boundary. Okay, boundary zone between two plates, the edge of a plate where it is in contact with another plate. That's what we call a plate boundary. Now, earthquakes occur along these plate boundaries, where two plates move relative to each other. And that's the map that you guys saw with the distribution of earthquakes. All those earthquake epicenters you saw there, those are plate boundaries. So now we're able to make this connection between earthquakes and plate boundaries. Plate boundaries, those tectonic activity, ultimately leads to earthquakes. So ask yourself, do you live next? And if you do, chances are you have earthquakes. Actually, you do have earthquakes. Chances are you felt an earthquake in your. That's why we have earthquakes near. This is why the west coast of the United States has earthquakes and not the east coast, because the west coast has a plate boundary. The coast doesn't have a plate. The east coast of the United States is in the middle of a tectonic plate. So that explains why east coast doesn't have earthquakes. So really interesting, isn't it? Now, how do we know they're moving? How do we know the plates are moving? Well, we can actually measure plate movement. Yeah, we using GPS. Using GPS, we can go to these benchmarks and measure coordinates, and then come back 10 years and see how much those plates have moved. On the map down here, you can see these vector arrows showing the direction in which plates move. So we can actually measure how fast these plates are moving. The faster the plate moves, the more earthquake activity it will have. Isn't that awesome? And with that, I end lesson 6. It's a little bit short, yeah, I know. But next week, or not next week, but next episode, we're going to go into the different types of plate boundaries. So that's going to be a fun one. As always, thank you guys for making it through this video. I appreciate you guys watching. Please like, comment, and subscribe if you haven't already. Really appreciate you guys checking out the YouTube channel. Again, merch is available. Follow me on all my socials, and I will see you guys